According to the University of Washington researchers, they estimated that kids watch about 2 hours of TV at daycare, and parents admit they allow their children to watch TV for about 1 to 3 hours a day at home. According to the researchers, preschoolers are awake 12 hours, and their TV watching accounts for approximately 1/3 of their awake time. So we have 10 hours of TV per week at daycare and 11 hours of TV a week at home, for a total of 21 hours of TV each week. Suppose the distribution of the children watching TV is normal, with a mean TV watching of 21 hours with a standard deviation of 4 hours. We want to compute the following probabilities. So I want to read through these, and I want to highlight a few things here, because each one of these are going to be a little bit different in their own way. So first it says, if we randomly select a child from any daycare in Seattle, Washington, the child watched between 17 and 23 hours of TV during the week. Now keep that one in mind, and let's take a look at B. If we randomly select 6 children, what is the probability that the mean number of hours the children watch TV is greater than 25? Now just take a look at A and B and compare and contrast. And compare and contrast A and B. Does this one give a sample size in A? No. Notice that this one just asked, what is the probability that they watched between 17 and 23 hours. Notice that this one's asking the probability that the mean number of hours. So this one is asking a probability question based on selecting a kid out of the population itself. This one, part B, is asking a probability on X bar, because it says the mean number of hours. I want to point that out, because this is how you determine whether you're going to use X or X bar in your probability statement. David? Yes. If you're given a sample size and it says the mean number, and usually they work in conjunction, because you have to have N to ask a probability statement regarding X bar. Notice this one. If we randomly select 5 children, what is the probability that the mean number of hours watched is less than 18 hours? So can we agree then that A is asking a probability statement on X? B and C is a probability statement regarding what? X bar. So writing this in random variable notation for part A, this one is asking us to compute the probability that 17 is less than X is less than 23. Using random variable notation, part B is asking us what? The probability that X bar is what? Greater than 25. And part C, again, writing the probability statement, this is asking us to compute the probability that X bar is less than 18. Well, let's do it. So let's note the following. We're going to define X as the number of hours of TV watched. So we know that X is distributed how? How? Normal. Again, the normal takes 2 parameters. The mean is 21. and the standard deviation is 4. Now remember, we said earlier that x bar is distributed how? Sorry? X bar is distributed normal. And the mean for x bar is going to be what? 21. And the standard deviation for x bar is going to be sigma 4 divided by the square root of n. So it depends on which one of these two we're looking at. So for this one, it's going to be the square root of 6. And for part C, x bar, let me write it down here, then is going to be distributed normal with a mean of 21 and a standard deviation of 4 over the square root of 5. So let's answer part A. We discussed this earlier. So for part A, we have that the probability then of 17 is less than x is less than 23. So now that we have this, our next step is to what? Standardize. So this is the probability of 17 minus 21 divided by 4 is less than x minus 21 over 4 is less than 23 minus 21 over 4. So when we compute this, I came up with negative 1 is less than, this middle term now becomes z, which is less than 0.5. So again, if we draw our picture, again centered at 0, so we go from negative 1 to 0.5. So we know that we have to shade this region here. Since we have between two scores, we're going to use which method? The answer I'm looking for is upper minus lower. Okay. So if we look up the upper at 0.5, you will come up with 0.6915. If you look up for a z-score of negative 1, I get 0.1587. Taking the difference, I get 0.5328. 0.5. Okay. Good to go? All right, let's take a look at part B. Did I hear something? 0.5328. Now this one was a probability statement on x bar, so the probability statement we came up with was x bar then is greater than 25. And let's recall further that we said that x bar was distributed normal, 21, 4 divided by the square root of 5. So to help us out, when we go to standardize, yes, square root of 6, thank you, Bill. Now when we go to standardize our random variable, when we're using x bar, we still use the form, in the form z equals x minus mu divided by sigma, but sigma for x bar, so z sub x bar, we're going to use x minus mu times the square root of n divided by sigma. Because all I have to do up here is to substitute sigma over the square root of n in the denominator. And it's a fraction, so remember you invert and multiply. So when we're working with x bar, you need to remember this. So now we need to, since we have our probability statement in terms of x bar, it's the same process. The next step is to standardize. So we go the probability of x bar minus 21 times the square root of 6 divided by 4 is greater than 25 minus 21 times the square root of 6 divided by 24. Up to 21. See, I told you I was having mouth, brain, and hand issues here. All right, so this is the probability, and now this part here becomes z sub x bar. So this guy is z sub x bar is greater than It's not letting me pull my calculator up. So here we get 2.45. So again, if I draw my picture, this is asking this upper-tailed probability here, where this is 2.45. So if we pull up our z-table, remember the area is given us to the left, so we know we're going to have to take this area and do what with it?
Subtract it from 1.
Subtract from 1. Or, since it's an upper tail probability, can we also use the symmetry property and look up z is negative 2.45? So using the symmetry property, negative 2.45 is 0.0071. So we know that this probability now is 0.007, I believe. So that's using the tables. So now let's take a look at this last one, but let's use the calculator to do the last one. You guys have all this down? All right, so again for part C, we have that x bar is distributed how? Everyone, normal, with a mean of 21 and a standard deviation of 4 over root 5. So this is asking us to compute the probability that x bar is less than 18. Okay. So let's use our technology, and let's just recall that this is going to be normal CDF. Lower bound in this case is going to be what? The lower bound in this case is going to be negative infinity, right? Which is negative EE 99. The upper bound is 18. The mean 21, and the standard deviation 4 over root 5. So entering this into the calculator, if it'll let me, ta-da! So second distribution, normal CDF. So negative EE 99, comma 18, comma 21, comma 4 divided by the square root of 5. Close the square root, close the normal, press enter. So 0.06 0.068, 0.0468. How about that one? 0.0468.